If a skyscraper fails, I mean, it is an absolute catastrophe.
Hmm.
But you can't exactly cut a 50-story building open to check if its bones are healthy.
Right, yeah. Usually when we talk about checking up on a patient's health, there is this expectation of exploratory surgery. Like, if you really want to know what's going on inside, traditionally, you'd make an incision.
Yeah, exactly. But today in medicine, we don't do that as the first step, right? We have MRIs, we have X-rays, we have ultrasounds.
Exactly. The goal is always to look inside without causing any further damage. I mean, it's the entire foundation of modern diagnostics. You gather the maximum amount of internal data with, well, the minimum amount of physical disruption.
But then you step into the world of colossal engineering. We are talking about massive pressure vessels and refineries, miles of high-pressure steel pipelines, suspension bridges. And you realize we have to do medical checkups on these things, too.
Yeah, and doing physical destructive tests on those items would completely compromise the very structure you are trying to evaluate. You would literally be destroying the bridge just to prove it was strong enough to hold cars, which, makes no sense.
Which brings us to our mission for this deep dive. Today, we are cracking open a highly technical, honestly, completely fascinating document. It is an actual scope of work for non-destructive testing.
Yeah, and you'll hear us refer to that as NDT throughout this discussion.
Right, NDT. And this particular document is governed by the FEI Red Book 2017 edition. Now, for those of you listening who don't spend your weekends reading international construction law,
Which is probably most people.
probably, the FEI Red Book is essentially the global standard for managing massive, multi-million-dollar construction contracts.
It is. The FEI framework is the rule book.
Yeah.
What's really fascinating here is that this NDT document, it doesn't just tell us the physics of how to test a building.
No, it really doesn't.
It reveals the invisible safety net that keeps our modern infrastructure from collapsing. It's this incredible blend of high-end physics just directly colliding with rigorous contract law.
Okay, so let's unpack this. Because before we get into the really cool lasers and gamma rays, I mean, we have to understand the legal arena.
Definitely.
Because you cannot just walk onto a high-security construction site and start x-raying things whenever you feel like it. So lay out the ground rules for us. At the end of the day, who is actually responsible for making sure a building doesn't fall down?
So under the FIDC Red Book, specifically subclause 4.9, the primary responsibility falls squarely on the contractor.
Right.
They are the ones physically building the structure, and they are legally obligated to build a quality management system, or QMS, to prove they are doing it right.
So the contractor is essentially in charge of their own quality.
Yeah.
But, I mean, there has to be a check on that, right? You can't just have someone grading their own homework without any oversight.
Well, the contract anticipates that exact conflict of interest. And that is where the role of the engineer comes in. In this contract framework, the engineer represents the employer, so the person or entity actually paying for the project. Under subclause 7.3, the engineer is the ultimate auditor.
Oh, okay.
Yeah, they have the formal right to inspect, examine, and crucially reject work.
Wait, let me make sure I understand this dynamic. The contractor is essentially forced to grade their own homework. Like, they have to run all the complicated tests.
Right.
But the engineer is like the strict principal who can just pop into the classroom unannounced to make sure nobody's cheating.
That's a good way to put it. The underlying philosophy is trust but verify. The contract assumes the contractor is capable because they won the bid in the first place.
Sure.
Major construction, however, it demands rigorous, documented proof at every single step. And they manage this dance through a document called the Inspection and Test Plan.
The ITP.
Right.
I was looking at this ITP section, and it dictates exactly when the engineer gets involved in the testing process.
Yes, very specifically.
It uses these specific markers. There are review points where the engineer just looks over the paperwork later on. Then there are witness points where the engineer is formally invited to stand there and watch the test happen.
Yep.
And then there are the big ones, the hold points.
Oh, yeah. Hold points are serious business in construction law. At a hold point, work physically stops.
Wow.
The contractor cannot pour the next layer of concrete. They can't weld the next section of pipe until the engineer reviews the test results and formally approves them in writing.
I can only imagine how stressful a hold point is on a massive site. I mean, where every single hour of delay costs an absolute fortune.
It's immense pressure.
What happens if they're behind schedule? Can they just, skip a test to catch up?
Absolutely not. The contract is incredibly rigid on that front. Any change to the NDT program is treated formally as a variation under Clause 13.1.
Oh, so it's a whole legal process.
Exactly. You cannot unilaterally decide to skip a test just because the schedule is slipping. The legal framework is unyielding because, frankly, the physical consequences of a failure are catastrophic.
Man, that sets the stage perfectly.
Hmm.
So now that we understand the legal pressure cooker where these tests happen, let's talk about the physical tools.
Let's do it.
According to the scope of work, the first step is always starting on the surface. But what makes visual testing different from me just walking around a steel beam with a flashlight?
Well, it is highly regulated staring. The document is incredibly specific. For direct visual testing, the contract mandates you must have a minimum of 500 lux of white light illuminating the surface.
Okay.
And your eyes have to be within 600 millimeters of the target, and your viewing angle cannot be less than 30 degrees.
That is incredibly specific. It's not just a passing glance, it's a mathematically defined observation.
Precisely.
But what if they're inspecting the inside of a narrow pipe where they can't physically fit their head?
Then they utilize remote visual testing. This involves like borescopes or tiny video probes navigated deep into confined spaces.
Oh, like a medical endoscopy.
Exactly. But visual testing, even with a camera, it only gets you so far. It only reveals what is completely obvious and open to the surface.
Right, and here is where it gets really interesting for me. What if there is a crack on the surface of a weld, but it is so microscopic you physically cannot see it, even with that 500 lux of light?
That is when the toolkit moves to PT, or liquid penetrant testing.
And the mechanism here is brilliant. I mean, it relies on something called capillary action.
Yes. For solid, non-porous materials, inspectors first clean the surface perfectly. Then they apply a liquid penetrant dye, and the contract mandates they let it sit for a specific dwell time, which is a minimum of 5 minutes.
Wait, explain this capillary action to me. Is it just like gravity pulling the liquid down into the crack?
It is actually the opposite of gravity in some ways. Capillary action is the same physical force that allows trees to pull water from their roots all the way up to their highest leaves.
Oh, wow.
Yeah, it's the ability of a liquid to flow in narrow spaces without the assistance of, or even in opposition to, external forces like gravity. So during those 5 minutes, the liquid penetrant is actively pulling itself deep into any microscopic voids or fissures.
It's also like dropping food coloring onto a white ceramic plate. Like if there are tiny, completely invisible spiderweb cracks in the glaze, that food coloring just gets sucked right in.
That's a perfect analogy. And after that mandated dwell time, the inspector wipes away all the excess dye on the surface.
So it looks completely clean again.
To the naked eye, yes. But then they apply a developer. This is usually a chalky white powder.
Okay.
The developer acts like a powerful blotter or a sponge. It creates a reverse capillary action, sucking the trapped dye back out of the microscopic crack and spreading it onto the white powder, magnifying the flaw so it becomes highly visible.
That is genius. And the document mentions you can even use a fluorescent dye for this. So you apply the developer, turn off the lights, hit it with a UV light. What are the specs on the light?
The contract requires a UVA light emitting a minimum of 1,000 microwatts per square centimeter.
And boom, any microscopic crack glows like a neon sign in the dark against the metal.
It is highly effective.
But the source material says PT has limitations, right? Like, if you were inspecting something magnetic, like standard structural carbon steel, you move to MT, which is magnetic particle testing. Magnets, tell me how MT works, because this feels like pure magic to me.
It's not magic, it's pure physics. The inspector takes an electromagnetic Yerk picture, a heavy, handheld metal horseshoe with a coil of wire wrapped around it.
Okay, got it.
They place it on the steel to create a localized magnetic field. Think of that magnetic field like a river flowing smoothly through the steel.
Okay, I am picturing a river of magnetism.
Right, so if the steel is perfect, the river flows without interruption. But a crack acts like a massive boulder just under the surface of the water.
Oh, I see.
The magnetic force cannot flow through the air gap of the crack, so it is forced to detour up and over the flaw, literally breaching the surface of the metal. We call this magnetic flux leakage.
So the magnetic field leaks out into the open air.
Precisely. And while the electromagnetic yoke is active and the field is leaking, the inspector sprinkles incredibly fine iron particles over the area.
Oh.
Those iron particles are instantly attracted to the invisible magnetic leakage protruding from the metal. They pile up right along the invisible crack, drawing a perfect physical outline of the flaw.
That is so cool. But there is a catch mentioned here, right? Once you turn the yoke off, the metal stays slightly magnetized, doesn't it?
It does, yeah. The contract states the metal must be demagnetized to below 3 millitesla, or 3 Gauss.
Why is that so important?
Well, if you leave a strong magnetic field in a steel pipe, it can interfere with future welding processes, like pushing the electric arc around unpredictably, or it could mess up sensitive electronic instruments installed nearby.
That makes a lot of sense.
Okay.
What stands out to me here, though, is how the choice of test is entirely dictated by the raw physics of the material. Like, MT is incredible, but if you are building a structure out of aluminum or austenitic stainless steel, MT is completely useless.
Exactly, because those materials are not ferromagnetic. You cannot induce that magnetic river. So for those materials, engineers are forced to revert back to liquid penetrant testing to find surface flaws.
Okay, so we have visual, penetrant, and magnetic testing. These are all phenomenal surface methods. They're great for finding cracks that break the outside skin of the metal.
Correct.
But let's say you have a piece of steel that is like 3 inches thick. What if there is a fatal air bubble or a lack of fusion hiding right in the dead center of that massive joint? I mean, surface testing is completely blind to that.
Totally blind. To find internal flaws, we have to transition to volumetric inspection. We need tools that look completely through the material.
Right.
And that brings us to sound, radiation, and electromagnetism.
Okay, let's start with sound, UT, or ultrasonic testing. Is this basically just a medical ultrasound, but for heavy industry?
The underlying principle is identical, actually. A transducer sends a high-frequency sound way beyond human hearing into the material. If the steel is solid throughout, the sound travels to the back wall of the material, bounces off, and returns to the probe. But if there is a hidden void, a crack, or an impurity, the sound hits that obstacle and bounces back early.
So it's all about timing.
Yes. By measuring the exact time it takes for the echo to return, the machine calculates exactly how deep the flaw is.
The source mentions the technology here has gotten incredibly advanced, too. There are all these acronyms, like PAUT phased array ultrasonic testing. How is that different from just sending a simple sound pulse? Like, how do you steer sound?
Imagine standing at the edge of a perfectly calm pond. If you drop a single pebble, you get a simple circular ripple, right?
Right.
That is standard UT. Now imagine you have a device that drops 64 tiny pebbles into the pond in a highly specific computerized sequence, just nanoseconds apart.
Well, the ripples would all crash into each other.
They would, but they crash into each other in a calculated way. The overlapping waves interfere, creating a combined, powerful wavefront that can be electronically swept back and forth through the metal without physically moving the probe.
Wow.
That is phased array. It creates a detailed cross-sectional image of the interior.
That makes perfect sense. And the document also mentions TOFD, time of flight diffraction.
Right. TOFD is another advanced sound technique. Instead of just listening for the echo bouncing directly off the face of a crack, TOFD listens for the faint diffraction of sound waves scattering off the very top and bottom tips of the crack.
Oh, so it measures the edges.
Exactly. It is incredibly precise for measuring the exact height of an internal defect, which is critical for engineers calculating if a flaw is dangerous.
And they can even change the shape of the sound waves themselves. Like, the document lists different wave modes depending on the geometry of the metal.
Yes, inspectors use longitudinal waves to measure thickness straight down, like a ruler. They use shear waves, introducing the sound at an angle so it bounces off the inner walls to inspect the complex geometry of a weld.
Fascinating.
And they use Rayleigh waves, which skim just along the surface of the metal like a torpedo. And even Lamb waves, which resonate through the entire thickness of thin metal plates.
It's literally an absolute symphony of sound.
Yep.
But then we have RT radiographic testing. This is the heavy artillery.
Right.
I mean, we are talking about shooting actual radiation through steel to expose a piece of film on the other side.
Not just radiation, but often gamma rays emitted by highly radioactive isotopes like iridium-192 or cobalt-60.
Wow.
Yeah, these aren't machines you just plug into a wall. They're literal glowing radioactive sources.
Which totally explains the extreme safety protocols in the document.
Yeah.
You are dealing with radioactive isotopes on a chaotic construction site. You have to set up massive radiation exclusion zones.
You do.
You have to deploy dedicated radiation protection supervisors. You essentially have to clear the entire area. But wait, I have a fundamental question about this.
Yeah.
If radiographic testing gives you a permanent, literal photograph of the inside of the steel, why bother with all the complex ultrasonic sound waves at all? Isn't a photograph always better than just listening to echoes?
Well, the scope of work actually addresses this specific limitation. A radiographic photograph is a two-dimensional shadow of a three-dimensional object.
Right.
It is only as good as the angle of the radiation beam. Radiography struggles severely to see planar defects, like incredibly flat, tight cracks, if they are oriented parallel to the beam.
Oh, I see. It's like holding a thin sheet of paper directly at eye level. Like if you look at it edge on, the paper practically disappears.
Exactly. The gamma rays pass right by the flat edge of the crack without casting a meaningful shadow on the film behind it.
That makes sense.
Furthermore, RT requires access to both sides of the object. One side for the radioactive source, the other side for the film.
Right, which you don't always have.
Exactly. Ultrasonic testing can catch those hidden planar angles by steering the sound waves, and crucially, it often only needs physical access to one side of the material.
So they basically cover each other's blind spots. Just to round out the volumetric toolkit, the document mentions ET, electromagnetic testing, which induces these eddy currents. The mind-blowing application here was PCT, pulsed eddy current testing.
Oh, PACE is an extraordinary piece of technology, used heavily in the oil and gas sector. It is used to detect corrosion under insulation.
Meaning you have a steel pipe carrying boiling chemicals. That pipe is wrapped in 3 inches of thick thermal insulation and then covered in a protective aluminum jacket. And this tool can measure the thickness of the steel pipe inside without removing any of the insulation.
It can. It creates a powerful, pulsing magnetic field that penetrates right through the non-magnetic insulation and the weather jacket.
Unbelievable.
It induces tiny electrical currents, eddy currents, in the hidden steel pipe. By measuring how those currents decay over milliseconds, the machine calculates the remaining wall thickness of the hidden steel.
That must save so much time.
Massive amounts of time and money, yeah, because you do not have to strip miles of insulation just to check for hidden rust.
Okay, so we have capillary dyes, magnetic flux leakage, phased arrays of sound, gamma radiation, and pulsed electromagnetism.
Yeah.
You can have the most advanced toolkit on the planet, but, I mean, it is entirely useless without a human being to interpret the data. Who is actually allowed to wield these tools?
This is where international personnel standards like ISO 9712 and ASNT come into play. NDT personnel must be rigorously certified.
Okay.
And the system operates on a strict 3-tier hierarchy, level 1, level 2, and level 3.
Let's break those down. Level I is the entry point, right?
Right.
The document states they can calibrate the equipment and they can physically perform the test, but they can only do this under supervision, and they absolutely cannot independently evaluate the results.
Right. They are essentially technicians gathering raw data. They do not have the authority to make a final diagnosis.
So if we return to our medical analogy, the level I technician is kind of like the phlebotomist drawing your blood. They are highly skilled at finding the vein and using the needle, but they don't sit down and tell you what your cholesterol numbers mean.
Exactly. That diagnosis is the responsibility of the level 2 technician. They are the absolute workhorses of the NDT industry.
Right.
They set up the complex equipment, they perform the tests, but most importantly, they interpret the results against the dense legal codes, and they sign the final reports. They are the doctors diagnosing the disease.
And then there's level 3, the masterminds.
The level 3 personnel rarely perform day-to-day field testing. They write the intricate testing procedures, they audit the program, they train the lower levels, and they take the ultimate technical responsibility for the entire system.
But wait, I have to push back on this limitation for the level I technicians. Let's say a level I technician is doing a magnetic particle test. They sprinkle the iron dust, and they are staring right at a massive, obvious crack on a critical structural beam. Are you seriously telling me they are not allowed to legally say, hey, this beam is broken?
Legally speaking, no. They cannot make that formal declaration. And it ties directly back to the legal framework we discussed in Section 1. In construction law, declaring something defective kicks off a massively expensive chain of contractual events.
Oh, because of the hold points and variations.
Exactly. You cannot have someone without comprehensive training and acceptance scores triggering that chain reaction. The active interpretation is strictly gate-kept by certification.
Man, it is wild to think about that level of bureaucratic control over physical reality. And speaking of physical reality, there is a literal vision test required for all of these levels. Like, it is not just a polite recommendation.
Not at all.
The document mandates that all NDT personnel must pass an annual near-vision acuity test. They specifically have to prove they can read something called Jaeger number 2 text at a distance of not less than 300 millimeters.
It really highlights how incredibly human this whole process still is. Despite the millions of dollars of ultrasonic equipment, you are ultimately relying on a human eye at exactly 300 millimeters to catch a flaw that could bring down a building.
Which brings us to the ultimate tension of the process, I think. The rigid legal framework collides with the physical realities of the testing. A level 2 inspector is scanning a weld. They find a major internal defect. It tells the standard. Um, what happens next?
This is the birth of an NCR, a nonconformance report. The contract states this formal legal document must be raised within 24 hours of discovering the failure.
Within 24 hours.
Yes. The engineer is immediately notified, and the defective item is physically segregated or marked so it cannot be accidentally used.
It's like placing a structural arrest warrant on a piece of steel. According to the scope of work, there are basically 3 paths to resolve an NCR. Path 1 is repair. You grind out the bad weld, you completely re-weld it, and then you have to retest the entire area from scratch.
Right. And path 3 is rejection. The flaw is so severe or the material is so compromised, you simply tear it out, scrap it, and start over entirely.
But path 2. Path 2 is the one that caught my eye. It is called use as is, or use as is sounds terrifying. You're telling me they find a literal crack in a structural support, and the contractor can just say, it's fine, and leave it.
Well, it sounds like a reckless shrug, but it is actually a deeply rigorous mathematical proof.
Okay, explain that.
The contractor has to perform what is called a fitness for purpose assessment.
Right.
Let's say you find a tiny porosity flaw in a massive concrete piling. If that specific piling only ever experiences downward compression force and never experiences tension, that would pull the flaw apart.
Right, because it's just being pushed down on.
Exactly. Then the contractor can use advanced fracture mechanics to prove the flaw will never grow or affect the safety of the structure.
Ah, so it's not ignoring the flaw.
Mm.
It is proving mathematically that the flaw is structurally irrelevant based on the physics of where it is located.
Exactly. But it requires the engineer's formal written approval to accept the concession. Furthermore, there is another massive consequence to finding a defect. The document calls it consequential NDT expansion.
Oh, yeah. This looks absolutely brutal for the contractor. Let's say the contract only requires you to test a random 10% sample of the welds on a 50-mile pipeline.
Right.
If you find a defect in that 10%, you can't just fix that one specific defect and move on. The rules force you to expand your testing scope. You might have to test the next 20% or even jump to testing 100% of the welds, entirely at your own cost, hunting for a systemic issue.
It is a brilliant built-in penalty mechanism. It forces the contractor to maintain impeccable quality across the entire project, not just on the isolated parts they suspect will be audited.
Yeah, that makes sense.
It ensures the statistical sample genuinely represents the overall quality of all the unseen work.
So let's step back and look at the vast web we have unpacked today. We started with the stringent legal framework of the FIDI Red Book, where the contractor bears the burden of proving their quality to the auditing engineer.
Right.
And we explored the toolkit-defying gravity with capillary action, mapping invisible rivers of magnetic flux, dropping pebbles of high-frequency sound to steer waves, and shooting literal gamma rays through steel.
And we discussed the rigid hierarchy of the certified personnel authorized to wield these tools, and finally, the legal mechanism of the nonconformance report when a flaw forces the entire massive machine to a halt.
It really is an incredible, invisible tapestry of science and law. So to you listening, the next time you're standing in a high-rise elevator or driving your family over a massive steel suspension bridge, take a second to think about the NDT technicians.
Absolutely.
Think about that level 2 inspector, hundreds of feet in the air, staring at a wavy line on an ultrasonic graph, or holding a radiographic film up to the light, ensuring the steel holding you up is sound.
It really provides a profound sense of comfort to understand just how rigorous and uncompromising that hidden medical checkup really is for our infrastructure.
It does. But I want to leave you with one final thought to mull over. Throughout this entire massive technical document with all its high-tech lasers and gamma rays, the final call on safety relies entirely on human interpretation.
Right.
It relies on a level 2 inspector's eyes passing that Jaeger number 2 vision test. But right now, in actual medical hospitals, we are seeing the rapid advancement of AI pattern recognition algorithms that can spot microscopic tumors on an MRI scan faster and more accurately than the human doctor.
Oh, that's a really interesting point.
So based on what we've learned today, how long until the algorithmic level 2 replaces the human in construction? How long until we only need the level I technician to physically hold the probe and the level 3 to legally sign the document, leaving the actual life or death diagnosis of our infrastructure entirely to a machine?
See the link in the description for free PDF download. Also, watch our other construction scope videos. Thanks for watching. Please subscribe and see you next time.